Okay, good. So I hope you can still see my whiteboard. Yeah, good. So I list the methods of proof, and then we majorly put a lot of weight on mathematical induction because it's the mostly applicable proof for this course, okay? But for the benefit of getting the knowledge on other types of proof, we'll still discuss them later on, okay? Yeah. So we have these uh, following methods of mathematical proofs. So we have what we call mathematical induction. Mathematical induction we can abbreviate by MI, or some people call it principle of mathematical induction. So when we say principle of mathematical induction, then we abbreviate it by PMI. So when we'll now be solving problems, I'll just be using the abbreviation PMI to mean principle of mathematical induction, okay? Yeah. And then another method of proof is called contradiction. Another method of proof is called direct proof. Another method of proof is called proof by counterexamples. Another method of proof that is of interest is also proof by cases. And then the other method of proof is also what we call proof by contraposition. So I want you to list those methods. Once you're done, you let me know so that we start. Okay. So the key method, okay, all the methods is you need to know all of them, but mostly in this course, what we dwell in mostly will be proved by principle of mathematical induction and then proved by contradiction. But we'll still discuss these other sorts of things. You need to deal with them. Okay. Yeah. So the proved by mathematical induction will give the statement and then see how to solve problems using that principle. So one, principle of mathematical induction. Principle of mathematical induction. So before I give the formal statement, I would like us to do an experiment about addition of odd positive integers. So consider, so this is an activity. Consider the set of positive integers, positive odd integers 1, 2, 3, 1, 3, 5, 7, 9, 11, etc. up to 2, n minus 1. So I want us to recall that when we say 2n minus 1, then that's the way we write a general positive. That's not necessarily positive, but that's how we generally write an odd number. So consider that list of odd positive integers. So I want us to do the sum of these numbers. So if I have only the first odd positive number 1, then the value remains to be 1. So I have 1 is just equals to 1. But if I pick 1 and I add to 3, what answer do I get? I get 4. Then when I pick 1, I add 3, I add 5, then my answer will be 9. So the sum of the first 3 odd positive integers is giving me 9. If I have 1 plus 3 plus 5, then plus 7, what do I get? 16. So that's the sum of the first 4 odd positive integers. And then if I have 1 plus 3 plus 5 plus 7 plus 9, sum will be 25. Then I can stop here. If I have 1 plus 3 plus 5 plus 7 plus 9 plus 11, what will be my sum? 36. So, and we can actually do, we can extend the same up to 1 plus 3 plus 5 plus 7 all the way up to plus 2n minus 1. So these are some of the first n positive odd integers. So to know the answer to the sum of the first n odd positive integers, we can actually give a guess from the previous result of some of the first terms. So if you only have 1, the answer is 1. If we have sum of the first 2, the answer is 4. The sum of the first 3, the answer is 9. The sum of the first 4, the answer is 16. The sum of the first 5, the answer is 25. And the sum of the first 6, the answer is 36. Are you able to see some pattern with those numbers? So what's the pattern? They are square numbers. Like when you only have one term, the answer is 1, so 1 can be written as 1 square. Okay? And then when you have sum of the first 2, the answer is 4, and 4 can be written as 2 square. Then when we have the sum of the first 3, the answer is 9, so this is the same as 3 squared. Sum of the first 4, the answer is 16, which can be written as 4 squared. And then this is 5 squared. This is 6 squared. So this being the first n terms, then we can guess that the answer to this will be n squared. So this guess of the sum of the first n odd positive integers being n squared from the previous few sums we have gotten can be proved by this method we are calling mathematical induction, whereby we are from the previous sums which are giving perfect squares. When we have n terms, we can actually try to guess the nature of the total sum. And the proof that the answer or the value we are guessing is true is confirmed by the method we call mathematical induction. So from a layman point of view, you see the way we have arranged this numbers or these sums here, it's like they are forming some stair. Are you seeing? Yeah, there's like we are forming some stair. So then now it's like for us to confirm that when now we have this sum of the first n odd positive integers is n squared, we need to confirm that when we start with the first number, only one term, the answer is true. And then we show that if we assume that now we have k of them, the value is also true. And then we show that now when we even add 1 to k, then the answer still have the same pattern of having a square. So we can say the proof, the technique, or not necessarily proof, the technique of proving that our conjecture. So where I guess in mathematics is called a conjecture, but our conjecture that the sum of the first n odd positive integers is n squared is a mathematical result. Is called not it's called mathematical induction. Mathematical induction which is usually applicable to proving mathematical results or theorems stated in terms of n n being a positive integer. Okay. Yeah, then now the process, we have not formally defined mathematical induction, we're just giving an intuition on how actually to know what the technique is all about, okay? Yeah. So probably maybe you can just, I'll tell you when to write, so that the key things, when you'll be giving the formal definition, right? This you can write after the class, okay? Yeah. So the process of mathematical induction may be compared to that of climbing an infinite staircase. So I'll draw it here. For example, this is a base or the ground, and then we have this staircase. I have this staircase, infinite. So you have this. Then we have this. Then we have this. So these are stairs, infinite of them. So for example, we have that case. So this is the base or the ground. So then now we want to see how someone can move, say, from this point A, ground, to say this point, say B. So what can assure a person should be able to climb this first stair? Are you able to see that? That if you are at this point, this point, okay, I'll wait just a minute. Let's watch win. It's called doing something. Yeah. So one, I think it's 1 to 9. Good. So if this person at this point A on the ground, so to move from A to B along this stair, for us to be for this person to move from A to B, the person should be able to climb the first stair. Yeah. So if you are able to climb to the first stair, then you can actually now move to the second stair, third stair, fourth stair, etc., up to say stair K. Let's say this is stair K. So if this K, let's this point here. So after moving after climbing the first stair, you go to the second stair, third stair, up to the K stair. Then once you are at this point K, when you are at this point or this stair K, then you should be able now to climb to the next step, which is actually the last step, part B. So this stair K, so this stair here. So first climb the first one, then you move along the same pattern, climb this one. Then if you're able to climb this one, then you can actually climb this next stair, which is K plus 1. Okay? Yeah. So then we can say from this diagram, in order to ensure that we complete the staircase, complete the climb, it is sufficient to ensure the following. So the first thing is that we need to climb the first step. We need to climb the first step or the first stair. So then now, once we have climbed the first stair, we reach a particular stair or step, say K, then we can always climb the next step, K plus 1. Because if you have actually moved from the first step, stair or step, we can do that for the second stair, then it is up to a stair K. Then if you are able to move from the first then to the second, then if you are at step K, then we can always move to the next step K plus 1. Okay? Yeah. So then now we can now give the formal definition. So this one now you can write. So statement. So let's PM plus 1, then PM plus 2, etc. Be a sequence of propositions. So let's have propositions PM, PM plus 1, PM plus 2, etc. So if one PM is true and PM plus 1, PK plus 1 is true whenever P of K is true, and this number M is less than or equals to K, then all the propositions are true in that sequence. So this is actually the principle of infinite mathematical induction. Actually, it's a theorem that if you have a sequence of statements or propositions P of M, P of M plus 1, P of M plus 2, etc., then if you are able to show that the first statement P of M is true, and you are able to show that P of K plus 1 is true whenever P of K is true, with M being less than or equals to K, then that is enough confirmation that the whole propositions PM plus 1, PM plus 2, etc. are all true. So this first one is called the basis. This one is called basis step. And all this combined is called inductive step. So this basis step and then this inductive step. If you are done, then you let me know so that I give you now a simpler version if we have just one statement. Once you are done, you let me know. Okay. Still not yet done? Okay, good. So then now, this is a principle of finite mathematical induction. Let's give the principle of finite mathematical induction. Then now we give a summary on how the steps need to follow, okay? So theorem, principle of finite mathematical induction. So let's P of M plus 1, P of M plus 2, all the way up to P of M be a finite sequence of propositions. So let P of M plus 1, P of M plus 2, up to P of N be a finite sequence of propositions. So if I 1, P of M is true, and 2, P of K plus 1 is true whenever P of K is true, and this K is between M and N, then all the propositions are true. So similarly, the first one is still the basis step. This is basis step. And then these two combined, we call it inductive step. So the only difference is that now here we have a countable number of propositions, Pm up to Pn. So write that statement. So once you are done, you let me know. Okay. Good. So then now we can now give a summary on the steps you need to follow to do mathematical induction. So in summary, mathematical induction is appropriate for proving that a result calls for all positive integers So to prove that a statement P of n is true by the principle of mathematical induction, we follow the following steps. So usually you will be given a statement and then they don't directly tell you that this is P of n. So what you do, you just say that what is given, you call it P of n. So yeah. So once you have given the name P of n, then the first step, verify or show that the statement P of n is true for n equals to n naught, where mostly n naught is taken to be 1. I'm saying show that n equals to n naught is true, because some cases will be given a problem whereby they tell you that show that this result is true for n greater than or equals to say 2. So then the first step becomes now you start at 2 going upwards. Okay. Yeah, but in most cases, will be n naught will be taken to be 1. But I'm just writing this one so that you clearly know that does not always mean that step 1 must be n equals to 1, because when the question restricts that show the result is true for, say, all integers n greater than or equals to 2, then your first step becomes you testing that the statement is true from n equals to 2. So yeah, so this step is called the initial step, or is called the basis step. So this is called initial or basis step. So once you have done that, and that one is very, in most cases, very direct to show that the statement is true for n equals to n naught, where n naught is 1 in most cases. So number 2, verify or show that the statement is true for n equals to k plus 1 whenever it is true for n equals to k, where k is a positive integer. I.e., this means prove that P of k plus 1 is true whenever P of k is true. We say that this step is called, all this combined is called inductive step, okay? Step, yeah. And this assumption that P of k is true is usually called the hypothesis. So that just say rewrite the same statement, but where there's n, you put k. So that is called the hypothesis, by assuming that P of k is true. So then now, lastly, if steps 1 and 2 have been established, then the statement P of n is true for all positive integers n. So that is what we follow. So, yeah, so then I want to give an example to illustrate how this process. This we had already, you had earlier written on. So just if you want to rewrite, you can leave some space to write later, okay? So what matters is how to solve the problems. Eh? Yeah. So examples. So prove by mathematical induction that for every positive integer n, positive integer n, 1 plus 2 plus 3 all the way plus n is given by n into n plus 1 divided by 2. So write that question. Good. So solution. The first thing you give the given statement a name. So we say let P of n be the statement 1 plus 2 plus 3 plus all the way up to n into n plus 1 divided by 2. So you give the statement given a name P of n. So what follows? P of k from just, yeah, we need to test that P of 1 is true. No. Yeah, so then now P of 1. P of 1 will be given by 1. This is the left-hand side of this equality. And P of 1 will be given by 1 into 1 plus 1 divided by 2, which is 1 times 2 over 2, which is 1. This is the right-hand side of that equality, okay? Yeah. And so since left-hand side equals to right-hand side equals to P of 1 equals to 1, the statement P of 1 is true, okay? So since when you only have n equals to 1, the left-hand side of the equality will give you 1, and when you substitute 1 for n on the right-hand side, you still get 1. Then we conclude that the statement is true for n equals to 1. Okay? Yeah. So next, we assume, yeah, we assume that P of k is true. So next, we assume the statement is true for n equals to k. That is, we have P of k is equals to, we're just writing the same thing, but where there's n, we put k, okay? Yeah, so we'll have 1 plus 2 plus 3 plus all the way up to n, up to k, equals to k into k plus 1 divided by 2. So that is the assumption that the statement P of k is true. So we rewrite the same original statement, only that where there's n, we put k. Have you done that? Okay, good. So once we have assumed that P of k is true, what should we show? Yeah, we need now to show that P of k plus 1 is true. So if that is the case, then we'll be done. So then we need to show P of k plus 1 is true. Okay? Yeah. By the P of k plus 1, we know the answer, how it's, we can actually guess the answer, how it should look like. But then we have to convince everyone that that's the correct structure. So if P of k is k into k plus 1 over 2, so what do you expect to be P of k plus 1? If P of k is k into k plus 1 over 2, so P of k plus 1 is expected to be? So the role of k is taken by k plus 1. We'll have k plus 1 into which will be k plus 2. So remember, when if you are at step k, the next step is k plus 1. Then from k plus 1, the next step is k plus 2, even. So yeah, so this will be k plus 2 divided by 2. So this is what you expect to have, okay? But then you don't conclude that that's the answer. So this just tells you that involving k plus 1 terms to reduce to this sum, okay? Yeah. So we can now begin rewriting the expression for pk plus 1. So P of k plus 1 will be given by 1 plus 2 plus 3 plus up to plus k. Then from k, I go to the next step, which is k plus 1. Okay? Yeah. But then you don't write equals to what we have actually said that the answer should be. So we need to show that we reduce this to that answer. Okay? But then from the previous step, what is the value of this sum? P of k. So this is P of k plus k plus 1. Okay? Yeah. But P of k, jibu yake ni? What is the condensed form of P of k from the previous step? What is P of k? Yes? Correct. So this is k into k plus 1 over 2, okay? And then plus this term is k plus 1, okay? So there's no mistake by us putting this over 1. So what is the LCM? LCM is 2. So hapa tutakuwa na k into k plus 1 plus 2 into k plus 1. So yeah. So your common is numerator. What is common? These two terms. k plus 1 into k plus 2 divided by 2. And this is really what we are looking for. As we say that's from the structure of P of k, then P of k plus 1 should be this expression, okay? Yeah, then once you have that one, this implies I'll give you time to copy this one. This one you can copy on, so you don't have to actually have pressure of writing. This one will be done after the class. What I want you just know the steps we need to follow through. So we'll have time to write this, okay? Yeah. So this implies that P of k plus 1 is true. So the validity of P of k plus 1 confirms the validity of P of n. So this statement 1 plus 2 plus 3 plus all the way plus n equals to m into n plus 1 over 2 is true. So that's the end of proof, okay? Yeah. So I want to give another. So I'll give you at the end of this one, you'll have time to copy. So don't worry. So what I want you to follow is actually to understand the steps you need to take, okay? Yeah. So problem 2, by principle of mathematical induction, prove that for all integers n greater than or equals to 1, if you take 1 squared plus 2 squared plus 3 squared all the way plus n squared, the answer is n into n plus 1 into 2n plus 1 divided by 6. Okay? So I want you to guide me on what I need to do from the start to the end. So, yes? Yeah, we give the given statement an MP of n, okay? Yeah, so we say let P of n be this statement, 1 squared plus 2 squared plus 3 squared all the way to n squared should be into plus 1 divided by 6, okay? Yeah. So that's the starting point. We give the given statement a name P of n. So what follows? We need now to show that P of 1 is true. So we show that P of 1 is true. And that one means that we need to show that when we have 1, both left-hand side and right-hand side will give us the same number, okay? Yeah. So left-hand side, P of 1 itatupatia 1 squared, which is 1, correct. And then let's see, the right-hand side, 1 into 1 plus 1 times 1 plus 1 divided by 6. So this is 1 times 2 times. How are you getting 4? What is 2 times 1 plus 1? 3. Then divided by, do you see that that's still 1? Yeah. So therefore we say, so since left-hand side, right-hand side equals to 1, then Correct. P of 1 is 2. So that's the basic step, okay? Yeah. So the next thing we assume that, yeah, so we assume that P of k is true. P of k is true. I.e., so P of k will be 1 squared plus 2 squared plus 3 squared all the way up to k squared should give us k into plus 1 into 2k k plus 1 over is true. So that one, you just make that assumption. We are writing the same statement, but when you can end tunaweka k. So once we have that one, what should we prove? Is true. So yeah, so now we need to show that P of k plus 1 is true. So usually what happens is that now we can actually know the expression that we expect to have P of k plus 1, because it's like just rewriting this formula, but when you kuna k unaweka k plus 1. So yeah, so we'll write P of k plus 1 will be equals to 1 squared plus 2 squared all the way plus k squared, then plus. Remember the pattern here, we are squaring terms. So then next will be now k plus 1 squared, not just k plus 1. Yeah. So no, you don't say equals to, you now reduce it for you to get what you want. So when you are doing this inductive step, you have to be very careful. You don't write the final answer. You need to reduce it so that now you get the final expression to agree with the same way P of k is. Okay. Yeah. So we say from this to this defines P of k. We have P of k plus 1 squared. Yeah. And what is P of k? K into 2k plus divided by 6. Then this plus k plus 1 square. Okay. So hapa tufanye nini? LCM. So tunaweza weka hii kama over 1, si ndio? Yeah, so LCM ni 6. So this will just be k into k plus 1 into plus 1 plus 6 into k plus 1 squared. Si ndio? Yeah. Sasa jiulize, what is common to these two terms in the numerator? K plus 1. So tutakuwa na k plus 1 outside into k into 2k plus 2 plus 1, then plus 6 into plus 1, okay? Yeah, because ilikuwa square initially, okay? So moja tumepeleka nje, so itabaki hapo just k plus 1. So what you do now, you open these brackets. So leave k plus 1 outside. So k times 2k, 2k squared, k times 1, k, 6 times k, 6k, 6 times 1, 6, and then divided by 6, okay? Kumbuka kuna over 6 hapa. Hapa juu kulikuwa na over 6. For this a fraction, okay? Yeah. So huku juu tutakuwa na k plus 1. So let's collect like terms. So tutakuwa na 2k squared. So k plus 6k, 7k, then plus 6 divided by 6. So this is a quadratic expression. We need to factorize it. So here, what is the product? 2 times 6, which is 12, okay? Sum, 7. Numbers, product is 12 and sum is 7. 1, 3, so 3, 4. So inamaanisha the expression 2k squared plus 7k plus 6 is the same as 2k squared plus 3k plus 4k plus 6. Ndio. Haya, sasa common hapa ni first two. What is common in this first number? K. So k into k plus 3. Then common in this other pair, k. 2 into plus 3, ndio. So hapa tutakuwa na k plus 2 into k plus 3, ndio. Yeah, so then now we can write this one is equals to k plus 1 into k plus 2 into 2k plus 3 divided by 6. But kumbuka, so that now we show that the p of k plus 1 is a two statement. P of k huko juu ilikuwa nini? Ilikuwa k into k plus 1 into 2k plus 1 divided by 6, okay? So what are we expected to have as our p of k plus 1? Nje tutakuwa na you can actually read it from this p of k, because the answer should become from this one here. When you replace where there's k by k plus 1, so what should be the first thing to write on the numerator? K plus 1 itachukua rule of k, okay? And then second bracket should have where there's k, you are putting k plus 1. Where there's k, when you put k plus 1, utakuwa na this place here ndio tunaweka k plus 1. So hiyo bracket yote itasimplify to. Yes? Mm. Mm. Yeah, because itakuwa this place itakuwa k plus 1 plus 1 itakuwa k plus 2, okay? And then we expect this other one to have 2, where this k we put k plus 1 and then plus 1. So, are you think that? But that's what we expect to have. So this will be the same as 6 is in the denominator. So juu kuna k plus 1. So that one you are okay with it because that was what we expected to have, followed by k plus 2, what we expect to have from this. But this other one, we can write it as 2 into k plus 1. So if I first here k plus 1, so 2 times k is 2k, 2 times 1 is 2 times 1. Oscar. Okay. Mm, mm, mm. Yeah, so that's what we have. So I'm saying that the 2k plus 3 can be written as 2 into k plus 1, then plus. Unaona why that is the same as 2k plus 3? Yeah, because when you multiply, you have 2k, then 2 times 1 is 2, 2 plus 1 is 3, okay? So this is our p of k plus 1, which actually we needed to have, okay? So then we conclude that this implies that p of k plus 1 is true. And still the validity of this one came from p of k. So therefore, by principle of mathematical induction, the statement 1 squared plus 2 squared plus 3 squared all the way plus n squared equals to n into n plus 1 to n plus 1 over 6 for all n greater than or equals to 1 is true. So, yeah, good. I know they are not, I still give more two examples actually to understand. Eh? Yeah, so, but you are the one to drive the process. So, question 3, use principle of mathematical induction to show that for any natural number, I hope you know that the term natural number is the same as positive integers. Eh? Yeah, for any natural number n, we have 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4. Dot here means product, okay? Yeah, plus up to 1 over n into n plus 1 is equals to n over n plus 1. I want to write that statement so that actually we'll be making reference to it. But in terms of writing the full statement, full solution, just write the expression the way the expression we need to prove. So that will be easier for us to make reference to it. So once you are done, you let me know. So you will just write the series and its value. Yeah. You can start, okay? So what the first step? Will be P of n. We give the name P of n, okay? And then after that, 1. Okay, tell me before before you give me the answer. Tell me what is the name of the step after giving the name P of n. So what follows? Basic step. So basic step, we show that now P of 1 is true, okay? Yeah. So we'll have let P of n be the given statement 1 over 1 times 2 plus 1 over 2 times 3 plus 1 over 3 times 4 all the way plus 1 over n into n plus 1 equals to n over n plus 1, okay? Yeah, then now we show that P of 1 is true. We show that P of 1 is true. So left-hand side, P of 1 will be 1 over times 2, okay? Which is over 2, just 1 times 2 is just 2, so half, okay? Yeah, right-hand side will be P of 1. Now where there's n, we put 1, okay? So we'll have 1 over 1 plus 1, which is 1 over 2, correct? So then since left-hand side equals to right-hand side equals to a half, then P of 1 is true. So we have done with the basic statement, okay? Basic step. So next step, we do what? Yeah, we assume that P of k is true. So we assume that P of k is true, i.e. P of k itakuwa nini? 1 over plus over 2 times 3 plus over times 4 plus up to 1 over into k plus 1 is true, okay? Yeah, so that's what we assume. Good. So once we have assumed P of k is true, what should we show now? Yes, we need to show that P of k plus 1 is true. So we need now to show that P of k plus 1 is true, okay? Yeah. So that's, I want you to tell me, P of k plus 1 will be equals to? Over? Plus over times 3 plus over 3 times 4 all the way plus over then what the next term? Over k plus 1 times hapana. So if this is step k, now step k iko na k into k plus 1. So step k plus 1 itakuwa k plus 1 into, yeah, k plus 2. From k plus 1 we go to k plus 2. So yeah, so that's what you'll have. So you don't now write the final answer. You are the one now to show that when you play with this expression, then it can give you a same formula, which is the same as what was obtained from P of k, okay? Yeah, so you define this one. This first k terms, its values. This is P of k, so I'll have P of k plus 1 over k plus 1 into k plus 2, okay? But what is P of k? Over into k plus 1. So plus, then this is 1 over k plus 1 into k plus 2. Okay. So, you know, this, we can have this this can be written as 1 over k plus 1 into 1 over k plus 1 over k plus 2. Are you able to see that that is the same thing as what you have in the, because ukisema 1 over k times 1 over k, 1 over k plus 1 times 1 over k is the same as what we have here. Ni kama nikupatia 1 over 2 times 3 can be written as 1 over 2 times 1 over 3. So, yes? After? Mm. We are finding the value of p of k plus 1. Now remember, ukiandika p of k plus 1, unafanya sum up to the k plus 1 term. Let me write the lines in terms of maybe letters for you now to reference clearly for me to understand what you're saying. So let's call this one 1, call this line 2, call this line. Okay, so you are saying line 2 is where you have line 1 or line 2, or line 2, line 4? Mm. 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 Yes. But by the you are right. So this is the same as k over k plus 1. The final answer for p of k. Okay? Yeah. Yeah, we needed to add that one. Hey, unaona mbali bwana. Kumbe huko unalala. Wewe ni mnoma. Yeah, thanks for saying that one in mapema. So that now when you have 1 over 1 times 2 plus 1 over 2 times 3 up to 1 over k into k plus 1, jibu yake ni k over k plus 1. Ndio? Yeah. So then that is what we need to replace here. Good. Wewe unaona mbali bwana. Ulikuwa nadhani unalala, kumbe ulali. Kumbe wewe ni mtu serious. Good. Yeah. So so I can actually, I'm sure that now people are following. So p of k yenyewe tukifanya jibu yake should be k over k plus 1, sindio? Yeah. So then now common here, we can see, we can now say maybe let's just put this thing under same LCM so that we don't confuse people. Just let's do it the way we have been doing the other problems. So now we combine these two fractions. But Ephraim, I hope you understand where the 1 over k plus 1 times k plus 2 is coming from. Yeah, good. Yeah. So LCM itakuwa nini? K plus 1 into k plus 2. Sindio? Ni kama tu mtu anakuuliza LCM ya 3 na 6. 6 is 2 times 3, so itakuwa 2 6, okay? Because this k plus 1 can divide all these things, can be divided, divide this number. So k plus 1 into this LCM, how many times? K plus 1 inaingia hapa mara ngapi? Yeah. It's like I'm asking you, what is this number divided by k plus 1? K plus 2. So ukijua k plus 2 times na k plus 1 unapata hii number, okay? Yeah. Then plus just 1. Okay? Yeah. So then now this, we can write it as k times k is k squared plus 2k plus 1 divided by k plus 1 into k plus 2. So what is the, remember this quadratic, now you factorize it. So product product is 1 sum 2 numbers 1 and 1, okay? Yeah. So hii tunaweza sema itakuwa k squared plus k plus k plus 1, sindio? So common here k into plus 1. Then common in k and 1 into k plus 1, sindio? Yeah. So this is the same as k plus 1 times another k plus 1, sindio? So hii tunaweza iandika kama k plus 1 times another k plus 1 divided by k plus 1 times k plus 2, correct? So this k plus 1 and k plus 1 cancels out, sindio? So tutabaki na k plus 1 over k plus 2. Do you see that that's what we expected to have? Yeah, because tulikuwa tumeambiwa that p of k ina reduce to k over k plus 1. So tukipewa p of k plus 1, yafaa jibu ikuwe juu inakuwa k plus 1 na chini inakuwa the next step, which is k plus 2. So this is our p of k plus 1. So we write the usual stuff, but this implies that p of k plus 1 is true, okay? It's true. So the validity of p of k plus 1 also comes from this p of k plus 1 is coming from p of k, the result of that, okay? Follows from that of p of k. So therefore, by principle of mathematical induction, the statement p of n is true, okay? Yeah. So I hope now when you are given problems on mathematical induction involving the sum of terms and the formulas, you should be able to try them. So now let me give you another version whereby it is not about sum, but it's just about some general statements which should be proven by still the same method. So the question is, use mathematical induction. This is example 4 or 3. Now the next one should be 4, okay? Yeah. So prove that 3 power 2n plus 2 minus 8n minus 9 is divisible by 8 for all integers greater than or equals to 1. So what I want you to write, I want you to write that so that I will be making reference to it. So just write the question and then how to get the answer. So once you are done, you let me know. In fact, even one person can write it so that now you can write it, and then once we have, then we'll be making reference to it. You'll actually you'll order your work after the class. Yeah, one of you can actually write it. Good. So then now to prove this one solution, we let p of n be the statement 3 power 2n plus 2 minus 8n minus 9 is divisible by 8. So So that is the statement we have, that expression 3 power 2n plus 2 minus 8n minus 9 is always divisible by. When we say divisible by 8 inamaanisha nini? Okay, give me an example of a number which is divisible by 8. 16, any other? Yeah, correct. So when you say divisible by 8 inamaanisha that number can be divided by 8 without a remainder, okay? Yeah. So when you divide that number by 8, you get a 0 remainder, or there's no remainder. So what is the first step? Once we have our P of n, we show that P of 1 is true, okay? Yeah, we show that P of 1 is true. So P of 1 is true mean that now where there's n, we put 1 and see whether the expression 3 power 2n plus 1 minus 8n minus 9 is a number which is divisible by 8, okay? Yeah, so P of 1 itatupatia 3 raised power 2 times 1 plus 2 minus 8 times 1 minus 9. So what is 2 times 1 plus 2? 4. So it'll be 3 power 4. 8 times 1? 8, then minus 9. And then can you tell me what is 3 power 4 minus 8 minus 9? First, what is 3 power 4? 81. So I'll have 81 minus 8 minus 9. Patia nini? 64, okay? Even a blind person can see that 64 is divisible by 8. Yeah, so which is divisible by 8. So that one is true, which is divisible by 8. So by replacing n for 1 in the expression 3 power 2n plus 1 minus 8n minus 9, then we are getting a number which we are sure that is divisible by 8. So that statement is, so the P of 1 is correct, okay? So by having that, then we say, hence, P of 1 is true. So we are done with the basic step, okay? So what is the next step? Yeah, we assume that P of K is true, okay? So we assume that P of K is true, i.e., P of K will be 3 power 2K plus 2 minus 8K, then minus 9 is divisible by 8. So that is how the statement will look like, okay? So we assume that this one is true. So then once we have assumed that P of K is true, what should we show? Is true, okay? Yeah, and that's the main work. Yeah, so I just wanted to write it. Yeah, so we assume that the P of K is true. So, and P of K means this expression is divisible by 8. So then now, next we show that P of K plus 1 is true, okay? Yeah. This step is usually where the main work is on the steps of proving by mathematical induction. So P of K plus 1 will mean we'll have 3 raised power 2. The place where we have K, we put K plus 1, okay? K plus 1 plus 2 minus 8 into K plus 1 minus 9. So we want to see if we play with this expression, we are going to get an expression which is divisible by 8, correct? Now, let's open this. This will have 3 raised power 2K plus 2 plus 2 minus 8K minus 8 minus 9. Do you agree? Oscar, are you seeing that? Yeah. So which can be written as, I hope you remember lots of indices that if I have a power m times a power n is the same as a power m plus n. So that we can always, if we have same bases, we can always add the powers. So we are going to make use of that one to simplify this first term, so that we write it as 3 raised power 2k plus 2 times 3 raised power 2 minus 8k. So minus 8, and then I have just write minus 8, and then minus 9. Then I can rewrite this one. Tell me, what was the expression for P of k? Was 3 raised power? So this can be written as 3 raised power 2, 3 raised power 2k plus 2 minus 8k, then minus 9, okay? Of course, this expression here. So I have minus 8. So I want you to be very keen here so that you see what is happening here. The reason as to why I'm forcing this expression here is because I already know that this number is divisible by 8 from what we have assumed in the previous step, okay? So we want now to balance this one so that it's exactly the same as the original expression, where we had 3 raised power 2k plus 2 times 3 raised power 2 minus 8k minus 8 minus 9. So, well, let's see how we are going to balance so that what we have written doesn't have a different value from the previous one. So the first term, 3 power 2 times 3 raised power 2k plus 2 agrees with what we have in the previous step. When you open the brackets, okay? Yeah. But then now here, I have 3 power 2 is affecting minus 8k. Are you seeing that? So it's like, by the 3 power 2 is which number? 9. So it's like I have 9 times minus 8k, okay? So how do I balance so that I don't affect the terms with k in the previous step? So if I was to open, I'll have now this one is 3 squared is 9. So it's like I have 9, what I have in this bracket here. 9 into 3 power 2k plus 2 minus 8k and then minus 9, okay? So hii nikiopen ni kama I have 9 times 3 raised power 2k plus 2 minus 9 times 8, 72k, and then 9 times minus 9, minus 81, okay? But remember, the previous expression is given by 3 raised power 2k times 3 raised power 2k plus 2 times 3 raised power 2, which is already 9, minus 8k minus 8 minus 9. So then, what should I do to this expression so that I have the same number in the first or the previous expression? So the first term, there's no problem. Do you see? So how do I convert minus 72k to be minus 8k? What should I do to minus 72k so that the value is minus 8k? No, we are not dividing. So what should I add or subtract to minus 72k? So remember, if you want to play with an expression, you don't divide. What you are allowed to do is to add or subtract. Division is when you have an equation, but this is an expression. So to balance an expression, you do add summation or difference to do the balancing. division or multiplication is only happens when you have equations. So I have minus 72K. What should I add to minus 72K so that I still have minus 8K? Can you find the value of this box in simple terms? 64K, okay? Yeah. Sasa nikiongeza hapa 64K, I'll be assured that there is no problem with actually terms involving K, okay? Here I have minus 81, okay? So I have this as minus 81 as the constant. But in the previous expression, what is the value of the constant? Remember, these are the two constants. Minus 8 minus 9 is what? By which value? Minus 17, okay? This constant involves this minus 8 and minus 9, okay? So when you combine them, is minus 17. So then ask yourself, what should I add to 81 so that the answer is minus 17? Minus 81 so that the answer is minus 17. Can you find the value of that box? What be? Positive or negative? Positive. You are sure? You are not sure. It's like I'm asking you, can you, if I call this bracket, I call it X. So what is, I have minus 81 plus X equals to minus 17. What's the value of X? Positive 64. So I add here 60. Okay. So then now it means that once I have first this bracket here, which we know is divisible by 8 from the previous step, then I need just to add 64K and I add 64. Then when I open the brackets, the value I have will be exactly the same as the previous one. Okay. Yeah. So that will be the that's how, and the reason as why I thought this bracket here is because from the previous assumption, we say that the expression 3 power 2K plus 2 minus 8K minus 9 is always divisible by 8, yeah. So 3 squared is 9. So I'll have this the same as, I can still write it just as 3 squared into 3 power 2K plus 2 minus 8K minus 9. Then plus, what is common here? 64, okay? Into K plus 1, okay? Then, are you able to see that this number, this and this, each one of them is divisible by 8? Can you convince yourself in that that the two are divisible by 8? Why? Yeah, P of K, which is always divisible by 8, okay? Yeah, so if one number is divisible by 8 and you multiply by another number, it doesn't matter the value of the number you're multiplying it. Provided one of them is divisible by 8, then the whole product is divisible by 8, okay? Yeah, and then the second part? Yes. It's also divisible by 8, correct. So then now we can say since, so this can be written as 9 times P of K plus, this can be written as, what is 64 divided by 8? 8 And then so we can have this one as 8, then K2, where K2 is the same as 8 into K plus 1. Okay? Yeah. And which is divisible by 8. Since P of K is divisible by 8, and 8K2 is also divisible by 8, okay? Yeah, it's also divisible by 8. So if you have a sum of two numbers, each one of them is divisible by 8, then when you put the when you combine them, the answer will still be a number divisible by 8. Okay. Yeah. So therefore, by principle of mathematical induction, 3 raised power 2n plus 2 minus 8n minus 9 is divisible by 8 for all natural numbers greater than or equals to 1. So I'm not introducing the other proof. The other proof we'll do maybe tomorrow. So I just want to give another example on the same thing. Then we stop. Then you should be able now to do other problems on induction. Okay. Yeah. So if we are able to reason out this one fully, then we can stop. So the other one is use principle of mathematical induction to show that for any integer n greater than or equals to 2, 3n squared is always greater than n plus 1 squared. So what I want you to write, just write this one, so because we'll be making reference to this. So this is the main thing, that you want to show that this 3n squared is always greater than n plus 1 squared for any given integer greater than or equals to 2. Okay. So Ephraim, what will be our P of n? Three n squared greater than n plus 1 squared. Correct. So that's the statement. So what's the first basic step? We'll be testing P of what? So P of 1 or P of 2. So which is which? Oscar, remember that we are saying that this statement, it is only true from n greater than or equals to 2. That's why we say that when you are stating from before we started giving examples on a principle of mathematical induction, we say that n equals to n. We show the first step is n equals to n naught is true. So n naught is usually 1, but sometimes it can actually change depending on the condition of the equation. Because about now, for this thing to be true, you need to have n greater than or equals to 2. So it will not hold when you start with a value less than 2, okay? Yeah, so then the base becomes, you start at 2 going upwards. Yeah, so step 1, show that P of 2 is true, because that's the smallest value of n that we need to start with, n greater than or equals to 2. So P of 2, left-hand side, will give us 3, 2 power 2, which will be? What the value? $12. And then right-hand side, P of 2 will be given by 2 plus 1 squared, which will be? Hey, boss. Okay, but 6 is a wrong answer, but at least I know where you're getting it. It was a square, not in product, okay? Yeah. So clearly, we can see that left-hand side is always greater than right-hand side. Yeah, 12 is always greater than 9. Okay? So then, and this is what we need to show, that the left-hand side of this statement is always greater than the right-hand side. So therefore, P of 2 is true. So that's the basic step. So remember, for this problem, it's not like the other problems where we're starting with P of 1. We start with P of 2 because it is a restriction given in the question that the given relation is only true starting from 2 and other integers more than 2. Okay? Yeah. So what follows? Yeah, so we let P of K, which is the same as, what will be P of K? Will be given as 3K squared greater than K plus 1 squared for any K greater than or equals to 2, okay? Yeah, let this one be true. So what are we supposed to show? We show that P of K plus 1 is true, correct, okay? Yeah. So then now let's see. P of K plus 1 will be 3 into K plus 1 squared, okay? Which can be written as, if you are to open the brackets, what is K plus 1 squared? K squared plus 2K plus 2 inatoka wapi bwana? Plus 1, yeah. So then those are signs that actually people are tired. So please, this is the last example. Give it your best, okay? I know you need to be taking lunch. This is the last example. Give it your best. I'm not writing any other example after this. So when you open, we'll have 3K squared plus 6K, then 6K plus 3. Good. So then now, this, we can complete the square for these terms in K. So I can have this one as 3 into, I can, remember we need to show, before I do that one, we actually have to foresee the relation we need to check for this step. If tumeambiwa P of K ni 3K squared should be greater than K plus 1 squared, then we expect our P of K equal relation 3 into K plus 1 squared should be greater than which square? K plus 2, sindio? Yeah, this is the relation that we need to confirm. So just leave this. So then now this can be written as, remember P of K is given by K plus 1 K plus 1 squared. So I can write this one as 3 into. So I want us to complete the square for this, but I can just have 3k, then plus 2, this k squared, then plus 2k, plus 1. So what should I add for me to balance? I want us to complete a square for that expression. So where I have now factored out 3, or maybe if you are not able to do that one, let me do it step by step. So the first 2 terms, 3 is common, okay? Yeah. So I can have this one as 3 into k squared plus 2k, then plus 3. That's the original expression, okay? So which I can write this one as 3 into, so I want us to complete the square for this one. So b is 2, okay? So b over 2, 1, okay? So I can write this one as k squared plus 2k. So 1 squared is 1, then plus, okay, really, I don't have even to open that one. So let's just leave the expression the way it is, 3k squared plus 6k. Let's leave it the way it is. And then remember, so after opening the expression for 3 into k plus 1 squared, this is the same thing as saying, so remember this is the left-hand side of the p of k, 3k squared itself. I'm able to see that 3k squared is the left-hand side of the p of k statement. Yeah, so this is where we have 3k squared. So then I can replace this 3k squared by p of k, and then plus 6k, then plus 3, because this 3k squared is the left-hand side of the statement p of k. So I can actually equate that to p of k. But you see, this expression will be greater than k plus 1 squared plus 6k plus 3. Why do you think that is the argument? We are saying that p of k plus 6k plus 3 will be greater than k plus 1 squared plus 6k plus 3. Why am I making that conclusion? Why are we making that conclusion that pk plus 6k plus 3 will be greater than k plus 1 squared plus 6k plus 3? Don't forget that this is what you say, that let p of k be this, to be a true statement. Remember that this is where we are basing our argument from this assumption. And the other one is on the right-hand side, okay? So left-hand side ndio iko na 3k squared. So you can replace hapa na p of k, inamaanisha when you introduce a k plus 1 square, then that value should be actually greater than k plus 1 square. Okay? Because hapa penye kuna 3k squared is the left hand side of the inequality of p of k. So kama nimesema 3k squared is replacing with p of k, then when I compare it with the other side of p of k, the right hand side, which is given as an inequality, then it should be actually be greater than, the value I have should be greater than k plus 1 squared, which is given on the right. Okay? Yeah, so that's why we are moving from this step to this step. But now here the changes from equality to inequality. So then now, can you tell me what is the value of k plus 1 squared? This is k squared plus 2k plus 1, then plus 6k plus 3. When you collect like terms, we'll have k squared plus 8k plus 4, okay? Now, these are quadratic expression. What is the product? 4, sum, 8, numbers. Numbers will be? Sum is 8, product is 4. Are there such numbers? You are sure? But we can force them to exist. But yes, there are no such numbers, but we can always force them. So what if we have, I write this one as k squared plus 4k plus 4 plus 4k. We will not have contradicted, we will not have changed the problem. It's still the sum is 8k. Okay? But if you split 8k as 4k plus 4k, it will give it the same value, okay? And then now we can actually do the factorization of this. So that now product is 4, sum is 4 for the first part. So inapatia nini? Numbers will be 2 and 2, okay? So then now we'll have k squared plus 2k plus 2k plus 4. So what is common in the first pair? K into k plus 2 plus 2 into k plus. So which is just the same as k plus 2 squared, okay? Remember for us to get the relation of p of k plus 1, we expected to have a k plus 2 squared in the inequality. Yeah, so inatupatia k plus 2 square, then plus plus 4k, ndio imebaki hapa juu, ndio? And by the we are dealing with which type of k? K is which type of number? K is which type of a number? From the start, when you are making this assumption. K is always greater than or equals to? Or equals to 2, okay? So if you have a positive, an integer greater than or equals to 2, what is the value of 4k? Is it positive number or a negative number? It's a positive number, okay? So then now we can say that this value, this quantity k plus 2 squared plus 4k is always greater than k plus 2 squared. Since k is always greater than or equals to 2. Okay? Yeah. So therefore now, hence, we have shown that P of k plus 1 is true. Yeah. So therefore, by principle of mathematical induction, then the result is true. Okay? Yeah. So at your own free time, you will try this. So these are questions for exercise. So using mathematical induction, show that for for any integer greater than or equals to 2, 3 power n is always greater than n squared. And then the other one, show that for any natural number, n, a power n minus b power n is divisible by a minus b, where a is always greater than b. Can I give you a hint on the second one? Yeah, so I can give you a hint for the second part, that the factorization of a power n minus b power n is the same as a minus b into n, a raised power n minus 1. Let me just write it here. So hint, recall that a power n minus b power n is a minus b into a power n minus 1 plus a power n minus 2b plus a power n minus 3 b squared, all the way plus a b power n minus 1 minus 2 plus b power n minus 1. So just this problem too, you solve it the same way we were dealing with the expression which was divisible by 8. That's the same route we'll take. And then problem 1, you take the same route we have taken for the previous example, okay? Yeah, so I stop there and then allow you to take lunch. So we meet tomorrow. Is it in the afternoon? Okay, good.